Cool. All right. Welcome, everybody, to the Intro to Container Security talk. My name is not Thomas Cameron. He originally submitted this talk. Unfortunately, he couldn't be here because of some health issues. So anyone in here who knows Thomas, he is doing well, but send some positive thoughts down towards Austin, Texas. I'm Ian Pilcher. I'm with Red Hat. I am a product manager in the OpenStack space. So I'm going to do my best to cover this slide deck. Basically, what we're going to talk about here is how Linux containerizes workloads. So we'll talk a little bit about what are containers at a very high level, and then dive into the various features and technologies within Linux that actually enable us to containerize workloads and build a container that then provides the isolation, the security, and the benefits that we get from those. This deck was created originally for a much longer time slot, so it is going to go pretty fast. So just first off, very broadly, what are we talking about when we talk about containers? Really, we're talking about a process or a group of running processes that have a restricted view of the system on which they are running. So they can't see all the resources of the host system, and they also have limited access to those resources. So we can limit them from, what they can access in the file system, CPU, memory, IPC, network, etc. And we'll talk about the ways we do that. Obligatory, what are containers not? They are, of course, not the answer to all problems. Some things are suitable for containers. And you can see with the various efforts that people are doing around things like container native virtualization or KubeVirt and Kata containers, etc., that there's ongoing efforts to bring more and more applications and workloads into sort of a container ecosystem. But still, of course, not the answer to all problems. There's still going to be a role for virtualized workloads. There's still going to be a role for just plain old bare metal workloads. And then sort of looking forward beyond that, things like serverless and lambdas, etc. And then finally, containers are not virtualization. I think, if you've followed the announcements around clear containers and now Kata containers, the fact that there are folks that feel the need to add virtualization to containers really confirms that. Containers in and of themselves do not give you the same level of isolation that virtualization does. So diving into the technologies that we use, and one of the big ones is kernel namespaces. So what kernel namespaces do is give the processes that are running within a particular namespace a limited view of the resources in that namespace. So I've got listed here the various ones that within Linux, and we'll talk about each of them individually. But by using these, we can create a view of the host system where we have very fine-grained control over exactly what the containerized process can see and what it can't see. So we'll start off with mount namespaces, and what mount namespaces do is they allow you to change the containerized process's view of the mounted file systems. So the easiest way, at least the way I think of this, having been using Linux for quite a while, is this is sort of the chroot on steroids, if you will. So it changes the root file system, but unlike, say, a chroot, if you had a chrooted process and it was able to access, say, proc mounts, in your proc file system, it would still see all the mounts that the host OS had mounted, where with a mount namespace, we give a consistent view. The kernel actually provides this consistent restricted view to the containerized process. Once we've done that, once we've taken whatever file system we're going to use as the root file system for our container. It's often, it might be a persistent volume, often an overlay file system, something like this. We then use bind mounts to very selectively make bits of the host file system visible inside the container. So we'll often mount, either directories or individual files from dev, etc., into the container, because a lot of applications often rely on being able to access those things in order to function properly. So here's an example. We're going to run, you see the command on top, we're actually running bash inside an Ubuntu container. And if you look at the output of the mount command from inside the container, you can see, if your eyes are better than mine and you're sitting close to the front of the room, the various file systems that make up those containerized processes' view of the world. Okay, so moving on, another namespace that the kernel provides are PID namespaces, or process IDs, and that, again, gives it a containerized process, its own view of the PIDs. And what this normally looks like with running containers is you will see, a process in there running as PID1. If you're running a Apache container, you'll see HTTPD as PID1, as an example. And normally on the host OS, of course, PID1 is going to be systemd, or whatever init daemon you happen to be using in your distribution. With the PID namespaces, here we can see in our container, PID1 is bash, and then PID6 is the PS command that was just running. This is the host OS view. So from the host OS, you can see that the bash is actually 18,613. But the namespace maps that to PID1 from within the container. Next up is user namespaces. And what this allows you to do is map usernames and user UIDs, as you might imagine. As it says here, very useful for multi-tenancy, and of course allows a UID 0 to run inside a container that is not UID 0 externally, which can be useful at times. So we see that here, where UID 0 has actually been mapped to UID 10,000 on the host OS. Network namespaces. Since we're at OpenStack Summit, so how many folks in here have worked with Neutron, and specifically the OVS ML2 Neutron plugin? So you all are going to be familiar with network namespaces. You're going to be familiar with the QRouter and QDHCP network namespaces that Neutron creates on your networker nodes, which allows them to have their own routing tables, their own firewall rules, duplicate IPs that actually correspond to different tenant networks, and all the magic that Neutron does to allow all the tenant networks to coexist, even with overlapping IP ranges. Let's see what we see here. So you can see here, we've got an IP address assigned to our container, and you can see inside, let's see, outside the container, you can see we don't actually have that IP address on that interface. Okay, IPC namespaces. So I personally don't do a lot of System 5 IPC, but things like System 5 shared memory regions, System 5 semaphores, etc. Obviously, these are shared resources within the operating system. So again, if we want to containerize applications, if we want to restrict their view and access, we need to be able to control what they're able to see. Come on, there we go. So here we see a containerized application, in this case, isn't showing any System 5 IPC resources, but same system, the host OS has a bunch of them that are created by various daemons, etc. UTS. So UTS is a fairly simple one. It simply allows a name application running in a namespace to have separate host name and fully qualified and short host names. So there we go. You can be that on the host OS. Come on. And within the container, have a lovely randomly generated host name there. So that's namespaces. Pretty quick blast through that. Hopefully it made sense. Control groups. So are often called C groups. So control groups are a technology within the Linux kernel that allows us to place limits, either hard or soft, on the system resources that can be consumed by, again, a set of processes. So those can be things like amount of CPU, amount of memory, amount of swap, disk I/O, maybe network bandwidth. Not sure if that's in there or not. So you can group your processes together. You can create a group of controls and apply that to the process or a group of processes. Basically, by limiting the resources, of course, this allows us to address the noisy neighbor problem. So if a particular containerized application, starts just consuming all the CPU, in the world, starts fork bombing, starts, allocating memory crazily, that will be isolated to that container and limited. All right. And systemd does actually create what it calls a slice, which is essentially a set of control groups for the services that it manages. Now, normally those don't have any controls applied to them by default, but anyone here who's using a systemd-based distribution, if you do a systemctl, whatever service, you will see the slice there. So it is all ultimately using this subdirectory under sysfs in order to control, manipulate, examine them. As this says, there's a ton of stuff under here. So this is not something you would want to do manually. You really want tooling to manage this for you. So yeah, 8,584 on this particular version of the operating system. So here we're just looking at a particular group and looking at some of the controls that have been applied to it. So perf events, how much CPU it can use. Some of the Docker slices, I don't even know what those are. PID, that's limiting the number of process IDs, so that's going to control your fork bomb, etc. And here I think, yeah, we're going to set we're going to look at the memory limit. So this, if I'm doing my math right, that's maybe 10 megabytes or maybe a gigabyte of memory that this slice is limited to. And we're going to start running, consuming as much memory as possible here. And boom, we get an OOM message. The OOM killer comes in, kills that process when it has, when it goes beyond its limits without impacting the rest of the host. Okay. Another technology is Linux kernel capabilities. So what Linux kernel capabilities are essentially is taking the privileges that we normally associate with a root user and dividing them up into groups that can then be applied or not, given or not given to a particular process. So there's like a cap-raw socket is one that I've used in the past. So if you wind the clock back far enough, you would see that the ping command on your system would have been an SUID executable because it had to have root access in order to create the raw socket that it needs to send out ICMP messages. Now we can just give that executable cap raw socket, and it does not need to be root. There's another one that will allow you to like bind to ports less than 1024. There are various other capabilities baked into the Linux kernel. So within container runtimes, and in this case we're particularly going to talk about Docker in this slide, you can actually apply a mask to a particular container. You can define exactly what capabilities processes running within that container will have, and what capabilities they won't have. So there, I guess, is the source code for how that is actually done. Next up is SELINUX. So question, of course, how many of you in here are running on a distribution that includes SELINUX? All right, how many of you have turned it off? All right, please send me your email so I can berate you properly. Stop doing that. It's been around for 15 years. It's not that hard. Turn it on. Anyway. So what is SELINUX? It is a mandatory access control system, of course. It works by labeling objects within the operating system. So we see that most of the time with files and various file system objects that will have a type associated with them. But they're also applied to things like network ports and a few other resources within the kernel. And then you write rules that say, subject, verb, object, that a process, domain in the SELINUX parlance, that is running with this context, if it wants to do this to something in this context, is allowed. You don't really need to write rules about what's not allowed, because by default, nothing is allowed. This is, of course, why if you really mess it up, you end up with a system that doesn't work at all. But fortunately, we provide a policy that works very well. So let's see. So you can have these various types. The label is actually not just a type. It's user, role type, and category that we're going to be talking about. There's also the idea of what they call multi-level security. If you actually have sort of a hierarchy of levels, which we usually, think of in like the public sector space, where you've got secret, top secret, so secret it doesn't even have a name, where one sort of implies the other. That's the multi-level security. That's not used very commonly out in the wild. But we do use the type extensively, and we use the category. So just a note, for file system objects, you've probably seen that the contexts are stored in extended attributes in the file system. And so this, of course, is if you're using a file system that doesn't support extended attributes. So if you ever have to mount a fat file system, NFS, etc., you just have to tell the kernel what context to use for everything on that file system. All righty, stop moving mouse. All right. So yeah, I'd mentioned user, role, type, and the multi-level, which we're not really gonna talk about, and multiple category. So gives an example here for if I've created a foo service, it'd probably have, just be user u object r, but it might be foo type, etc. And again, the default policy doesn't allow you to actually do anything. So we care about, and you write the rules to enable them to do anything. So we care about the type. Anyone who's worked with SELINUX, at all in enforcing mode has probably, gotten that message, that AVC message, and you see here's the source type, here's what it was trying to do, here's the object type, and then you go figure out, does it really need that? And if so, I enable it, or is this just, sort of a bogus requirement? There are a lot of times applications will try to do things, fail, and then continue on just fine. So we do use multi-category. So this is something we actually kind of pioneered in the virtualization space with a technology that Red Hat called SVirt. So we run each VM in our virtualization products under because it's a KVM VM is a process under Linux, of course, and it runs under a particular type, probably KVM type, I'm not sure. But then we wanted, and that isolates the VMs from the host OS. But if you just put them as, say, KVM type, then they would have access to each other's resources if they somehow were able to blue pill out of the VM. And we don't want that. So that's where we introduce the multiple categories. So we basically create a random category for each VM. So each VM would be a VM type, but then it would get its own category label. So we can then create rules that give that process resources to things that it might need, that a KVM process might need, maybe a few dev nodes or something like that. But then via the category, we prevent them from accessing each other's resources. And we do something basically the same within when we run containers. So we have types for the containers that we run, and then we add a category for each running container that isolates them from one another. Okay, so here we're going to use runcon. Runcon is just a command that allows you to run a process in Linux under a particular context to emulate an OpenShift container in this case. And we're going to try to look at Etsy Shadow. And you'll see we are not allowed to do that. That's SELINUX denying the permission there. Another technology is SECCOMP. And SECCOMP is not very commonly used in other contexts. What it essentially does is it allows you to apply a system call filter to a process and then to child processes. So that will limit the system calls that the process is actually able to execute, and it'll just get like a permission denied or operation not permitted, not sure which error. I believe that this is actually part of the technology. If you run Google Chrome, this is part of what Google Chrome does for its sandboxing. It uses SECCOMP for this. So, like I said, system call filtering messaging. We use a whitelist approach within the Docker daemon. So basically, we say you're allowed to, you Mr. Container, are allowed to do you can do a read, you can do a write. You can't do a chroot or various other things within that containerized context. So yeah, we're not going to let you load modules. We're not going to let you modify. Basically, we're going to try to avoid modifying the state of the global system. Okay. Within Docker, this is done via JSON files that define the policy for a particular container. And you can see an example of running one here, and again, getting the operation not permitted. So we've got all these technologies and all these settings and all these knobs. And wouldn't it be fun to sit down and write a bash script to run a process, with the appropriate virtual file system and bind mounts and SELINUX context and SECCOMP filters and namespaces, and I'm probably missing something. So what we need then is tooling to manage all this. And one of the, a very popular one, the one that that really kind of popularized containers, got them mainstream, was Docker, but certainly not the only one. So I actually gave a presentation very similar to this many, many years ago, talking about OpenShift gears, if anybody remembers the gears that we had in Red Hat OpenShift back before we adopted the Docker daemon. So Docker is one of them. Cryo, Rocket, I'm not sure. Scott's here, he knows. He can probably rattle off 15 or 20 of them. But what it does is it provides tooling to set all these settings, and then it provides a way to define what those settings need to be for a particular container. It has an image format that you can use to package up the virtual file systems that you want to use, and it will then take care of setting all these things up, starting, stopping them, etc. Few considerations when you are using Docker. It is a very privileged process. It is manipulating the state of your host at a very deep level. So you don't want to allow untrusted people to just SSH in and run Docker. That's why we have things like sort of higher level abstractions like OpenShift and other products to provide an interface for that with gives you the security and such around that. Obviously, if you're using the REST API, don't put it on the internet. Keep things patched. Common sense stuff there. Use TLS. Let's see. Few tips and tricks. Like this says, at the end of the day, a container is just a group of processes. Kill the processes, the container goes away. So things you want to do, you definitely want to keep your container images updated. This is maybe the number one, piece of advice or best practice here is you absolutely need to have a process in place to update container images in your environment. And quite honestly, it almost certainly needs to be automated. Because if you're using this in anger at all, you're very quickly going to have a lot of container images. It's not really going to be feasible to update those manually whenever there's an update comes out to any of the underlying layers. So anytime an OS, an update to a particular OS comes out, any container images built on that OS are going to need to be updated. That's a lot of updates. You've got to automate that. Just like we do outside containers, run your processes with the lowest privilege possible. Drop root privileges as soon as you can, or don't have root privileges at all if you can get away with that. Whenever you need to mount a piece of the host file system into the container, do it read-only whenever possible. Root inside the container is contained to a certain extent, but containers are not a panacea, so certainly anything running as root inside the container does still have a degree of elevated privileges. So you kind of need to think of it as root as you would as root outside the container. Definitely check your logs. Definitely enable no new privileges. Don't let it elevate privileges. Don't use privileged containers unless you absolutely need to. Use the capabilities masks that we talked about earlier. First bullet here, yeah, don't just pull things randomly from various registries out on the internet without knowing what the provenance is. Don't run SSH inside the container and let anybody log in who wants to. Avoid running with root, yeah. Don't disable SELINUX. Don't roll your own containers and just treat them as static objects. And if you've got production workloads that are important to your business, you want to run it on a supported platform, a robust platform, just as you would any other workload that is important to your business. All right, so in conclusion, despite some of the disclaimers, containers are an incredibly cool technology. They allow us to do things that we can't do with VMs. All those knobs give us fine-grained control over exactly how contained a particular container is, so it really allows us to tweak things and do things in the exact right way for a particular application and use case. So, go forth, containerize, but be smart about it. And with that, I'm actually a little surprised, but we've got a little bit of time for questions if anybody has any. Thank you.
Why not run SSH in the container?
Can you use the microphone?
Why don't you run SSH in the container?
It's just you're exposing it to the a shell in that container to the network in the same way as you would your host OS. So, I mean, any thoughts beyond that, Scott?
I don't have a mic, but you don't have to run it in there because if you're using something like Kubernetes, you can exec into it anyway.
Okay.
Without having to run a shell.
Yeah, I mean, and that's the other thing. It's hard to think of any reason why you would need to. So, yep.
So for the tool, if you want to use namespaces and C groups for other things, how mature is the tooling to do that?
So the C groups, if you're using systemd will carve out the slice for you, and it has tooling around setting up the controls on them. I've not actually used that. My non-container C groups experience predates systemd support for it. Back when I had to restrict the CPU utilization of cups on my fanless home system to keep large print jobs from melting it on CentOS 6. But it can be done with C groups. And the other one was namespaces. So network namespaces are fairly straightforward, I know. I mean, and I only know that from doing the Neutron stuff. I think in a lot of cases, there is command line tooling around doing it, so it can be done. I'm not really sure how difficult it is. I mean, obviously you'd want to eventually automate it. You're never going to want to do it by hand, but it can be done. Any other questions?
I would like to ask, other than the Docker container, what else the container technology available, and what's your recommendations?
So our recommendation. So my understand right now, I work for Red Hat. So all the Red Hat products that I know of that run containers right now are using Docker as of this moment. Kind of true.
OpenShift 3.9 has Cryo.
Okay, so Cryo is now is GA as an option. And do we want to say more?
I would say that all the images that we build are OCI compliant.
Right.
They'll run no matter what.
Exactly.
Cryo or Docker.
Yeah.
We try to use standards for everything.
Exactly. So keep your options open is definitely good.
We're also investigating other things.
Yeah.
It's a complex question. Run C underneath. There's things like C Advisor trying to, add in there. There's Kata. There's all these things that support OCI images. So as long as we have OCI images, we'll investigate everything.
So that's our recommendation: OCI compatible images. Yeah, it's a good point. Yeah, like I said, the answer in terms of exactly what command you use to run it may well change every year. So it's.
Well, the command should be OC run or.
Well, okay, yes, exactly. Use OpenShift. How's that?
Use OpenShift. And then we'll hide that complexity.
All right. Well, thank you everybody for coming.